We'll start the talk in a couple of minutes.
Hi, Claudia.
Hello.
It's Leslie. You probably can't tell in the sea of faces, but anyway.
I recognize your voice. I'm going through the videos, but it's hard to see you, to find you. Thank you for coming. I really appreciate it.
Sure. I'm excited to hear the story. I like your cartoon. Did you draw it?
I didn't draw it. I got some help from more skillful people at doing this. So I did. I hand draw sort of the idea, and they converted it into something.
That's good. Yeah, it's always good to have artistic friends. That's my strategy.
Most of the point is that the robot is building its own model here. That's what it tries to represent.
That's good.
Okay, awesome. Let's start the seminar now. Welcome to the first EA seminar of the spring semester. Today we have with us Dr. Claudia Pérez Darpino, who is a postdoctoral scholar in computer science at Stanford University, advised by Professor Silvio Savarese. Before that, she received her PhD in computer science with us at MIT CSEL, advised by Professor Julie Shaw, and she received her degrees in electronics engineering and masters in mechatronics from the Simón Bolívar University in Venezuela. She's working on robot learning for human-robot collaborative tasks in manipulation and social navigation. Her research focuses on hybrid learning as a framework for developing intelligent robots that can learn from observations, augment this learning with self-exploration, and apply the learned skills in interaction with humans. Welcome to the seminar.
Thank you for the introduction, Ferrana, and thank you for the committee of this seminar for inviting me. I'm super excited to be here today. So my name is Claudia Pérez Darpino, and today I'll be discussing topics on learning for human-robot collaboration. So there are some examples of scenarios in which human-robot collaboration has the potential to improve our lives. Robots are becoming more capable of learning and interacting with humans, and with these capabilities, they could perform side-by-side manipulation at home, navigate to move around people, for example, at home, malls, airports, and hospitals, and perform human activities in our environments. Another type of collaboration is remote manipulation, in which a human can directly control or supervise a remote robot. This can be useful at home, manufacturing, but also in disaster response sites in which robots can help us avoid sending humans to risky scenarios. All these scenarios benefit or can benefit from robots that learn how to perform tasks and fluently interact with humans in different capacities. So today I'll be discussing a series of works that I have conducted during my research and my PhD and postdoc so far in topics that are relevant to these scenarios. I'll start by discussing my work on learning manipulation from human examples, in particular in low data regimes. Then I'll discuss how to use this learned task to perform it with a human in the loop in a remote manipulation scenario. Then I will move into discussing how we can use simulation to get the robot further exploring the action and state spaces to get the robot to discover new ways of doing this learned task. Then I will have a little more conceptual discussion about the use of simulation on robotics and HRI as a segue from the previous work. And I'll discuss how I started exploring this topic in the context of social robot navigation. Finally, I will discuss briefly my ongoing work and some future opportunities that I see for embodied AI to help us understand some principles of intelligence. Great, so let's start with learning manipulation from human examples. So my inspiration in this topic starts from my experience in the DARPA Robotics Challenge. This challenge was about having a remote robot. Here you can see Atlas at MIT. deployed at a disaster response site, executing some mobile manipulation tasks that could be very useful. So here you can see Atlas moving or actioning this valve to open the valve. And even though if you only look at the video at the left, it looks like it is autonomous, it is actually being controlled by one or more highly skilled operators that you can see here at the right. So even though the DARPA challenge really made substantial progress in controls and perception, something that I remain with after this experience is the thought that it really had a limited actionable cognitive representation of the world. In other words, it is still hard for the robot to understand the goal and the scene and the context of the scene in the same way that we do. That's why the operators are the ones conducting the cognitive decision-making and understanding of the situation to make decisions. So if you look at Atlas in that video, what it is doing is going through a parameterized sequence of actions that were pre-programmed by an expert. So these actions are defined in reference to these objects, and you can think about them as a series of these steps or keyframes, and each one of these keyframes have been highly specified by somebody with a lot of experience. However, if we want robots to be able to act efficiently in the scenarios I described before, it would be great if they can instead learn these type of tasks directly from examples, or just in a more friendly way that doesn't require that robotics expertise to be programmed. So if you look at humans, we really can formulate task models from observing the task being done. And we do this effortlessly, usually, and sometimes from only one example. So in robotics, this is really the goal of the field of learning from demonstrations. However, in learning from demonstrations, the typical approach is to imitate at the geometric trajectory level. So that works for some types of tasks, but for others, it's really hard to adapt to different positions and orientations of the objects because the original trajectory, the geometric adaptation that you can do might not adapt very well. So here you can see the Optimus robot at MIT. It is faced with the task of grasping this handle at the left and then grasping the cylinder, the white cylinder, and extracting it. So this task is multi-step. You can execute it by the steps I just described. And furthermore, each step is geometrically constrained. So you can describe this task as a model of these steps and the constraints that you need to satisfy as you go through these steps. So I asked if we can learn this type of multi-step constraint tasks from human examples. And in particular, I was interested in looking if we can learn from a single example or only a few examples as opposed to a large amount of data. And I take inspirations from how I think humans do this. Something that I observed is that probably we are able to do this with only one example because we actually are already familiar with objects and how we typically manipulate objects. So the moment we see an example of a task, we're not just copying that, we are matching that with the priors that we already have about how we can execute subsequences of this task. So in order to try to replicate that phenomenon or that workflow, what I did is to separate my method into steps. This method is called C-Learn for constraints learning. So the first step in C-Learn is to collect a number of demonstrations of how we typically approach and grasp objects. So for each simple object like a cylinder or a box or a box, we take 4 or 5 demonstrations of how humans typically do it, okay? And the idea of taking those is that we're gonna build what I call a knowledge base. It's gonna be a knowledge base that we keep in memory, ready for later understanding a larger task. So to briefly describe how this process works is that we take a few demonstrations, and then we take the steps of the demonstrations and cluster them in space, in the space of the n effector. So if I provide 2 demonstrations, one from on top, one from below the object, we will discover that in the first cluster, maybe it wasn't very relevant to be constrained. You can be in all this space. So we are gonna assign a step that we call keyframe, And that keyframes has a sequence or a series of geometric constraints that can be used to represent that step. In the second keyframe, we were actually more constrained. Like you really need to be near the object, and you probably have to be parallel to some axis on the object and so on. So we will cluster that as a keyframe and query what of those constraints are active, and then assign a new constraint, a new keyframe with that set. So this is the type of model that we're gonna do for all the manipulation tasks. In the second step, the idea is to learn a multi-step task now from a single example. So we're gonna take a demonstration of the keyframes, for example, approaching the cylinder, grasping the cylinder, and then extracting. And we're gonna convert that demonstrated sequence into a sequence of keyframes of the form I described before. And what we're gonna do is to try to find subsequences that we know should be present on that knowledge base. Those are the examples of approaching and grasping objects. We are gonna segment that subsequence and substitute those keyframes with those from the knowledge base. And the reason to do that substitution is that actually the knowledge base has more variance because it was learned from a slightly bigger number of demonstrations. So it has more information about what was actually important. For subsequent steps in which we extract, what we can do is remember what the steps were with the additional benefit of checking what constraints were active. And then describing them instead of constraints instead of the entire trajectory. So at the end of the day, our model is going to be this learned sequence of steps and constraints that we can now use for a new scenario in which the objects might be in different positions and orientations. But since these constraints are expressed in terms of the frames of the relevant objects, we can now invoke an optimization-based motion planner. And for this, I use Drake to obtain a motion plan that satisfies these constraints to go from a step to a step, from keyframe to keyframe. So in this video, you can see 4 different tasks of the Optimus robot executing multi-step constraint manipulation tasks that would have been very difficult to learn with methods that only try to imitate full trajectories. My favorite task is this one of extracting the cylinder because it really has to obey that active constraint of being parallel to the cylinder as it is moving. An additional benefit of having this representation is that we are thinking really in terms of n effector space, right? And the part of how the body is going to move is being solved by the planner. That means that we should be able to transfer this into a robot with a completely different body. And we tested that with the Atlas robot in simulation, transferring without any additional demonstrations or any additional learning with the Atlas robot. We can transfer just the model of the constraints and now invoke the planner for this robot. Additionally, you can see that this particular one is bipedal and it has to keep standing, right? So you can write those additional constraints to be balancing for this particular robot, and those can be merged with the constraints that were learned in the model. So we not only transfer to a different body, but also to a different body with additional constraints. So that's a very brief description of how the method CLearn works. And now we'll move into describing how this model can be included into a model of human-robot teaming for remote manipulation. So in the video you saw before, Optimus is going through the sequence of steps autonomously. And that works, but we might also be interested in having a supervision or modifications from the human when we are talking about real scenarios on risky situations. One way to do that is to include a human in the loop to verify the motion plan or to perform modifications as the robot is going from a step to a step. So here, basically, the robot will query the planner to get a plan, which is displayed to the user or the operator in the form of an animation, so like a video game. The user can approve, reject, or modify the plan doing teleoperation, and then can send that for execution or in the real world, and then continue going from a step to a step. And this is similar to what we did for the DARPA Robotics Challenge, except that the model has been learned from demonstrations. So in order to assess the value of having this type of model for human-robot teaming, we experimentally compare with other teleoperation methods. And we conducted a user study with both professional EOD technicians and DRC robot pilots. Both groups are highly skilled robot operators. So I'll describe the conditions that we have to compare with. First, we compare with two classical teleoperation methods in which we have this device that is a complete kinematic replica of the robot. It's called imitation controller. So the user can just directly move the controller as the robot is moving simultaneously. And we have that with 2D and 2D plus 3D perception that you can see here on the screen. We also have a comparison with using the same interface that I described before, but you only have the ability to teleoperate the robot on the interface. So you go to the interface, you can only move the end effectors and to tell the robot how to move. That's condition C. And then in condition D, we have what we call assisted planning, which is having that teleoperation, but also having this sort of recommendations for motions that we get from the model that I showed before. So we compared these 4 different models to understand how having this assisted planning with the learned model was able to improve the task time and what benefits or problems it can bring. So in fact, we found that, remember the assisted planning condition is this last one, D. So condition D showed that it can achieve task times that are comparable to direct teleoperation, these first two. So direct teleoperation is probably the fastest that you can do. It is moving directly with you and you're providing these low-level commands. It also showed that it is significantly faster than using the same interface, but only with teleoperation, not the assisted planning. And something really interesting is if you compare the interactions between the two groups I described, the EOD operators or the DRC robot pilots, there is a significant interaction on the task time between the two groups. The DRC was significantly faster because this group has previous expertise with the particular interface. However, when you add the assisted planning using the same interface, you remove that interaction, resulting in a performance equalizer for the two groups, which is an important result that I think it's important to understand that you can have now with this kind of assistive technology, you can have groups with different expertise, domain expertise, but they don't necessarily have to be robot experts or interface experts to be able to achieve similar performance. So the results of the study are very extensive, and I invite you to check out the manuscript for looking at other results in terms of accuracy of the manipulation, as well as workload, TLX, and so on. So far, I think it was very positive to understand these results I just discussed. And we were able to achieve some generalization by having this adaptation to different positions and orientations of the objects, and also having the human in the loop able to perform some modifications to the original plan that the robot produced using the model. However, it wouldn't be able to really adapt beyond that, for example, to new topologies of the task or to new ways of doing the task, maybe changing the order of those keyframes or just simply completely different keyframes. So in order to pursue this further generalization, I decided to move into simulation a little bit to understand how we could further explore the state space and the action space to get the robot to discover new ways of doing the task that was demonstrated. So when you have a new scene and you want to generalize the model to that, there are a number of problems that can come. One of them is that the new scene can just render the original strategy just completely unfeasible. And that can happen both at the motion level or task level because of obstacles or reachability, just the robot simply doesn't get to the new position of the objects, or you may need new orders of steps or different steps. Another very interesting problem that I observe in just pure learning from demonstrations is that really the robot doesn't have this understanding of the intuitive physics of what's happening with the objects. So the description that it has in its mind is completely geometric. When it extracts the cylinder, it understands that constraints of extracting, but it doesn't have the notion of perhaps the cylinder falling after that because of the unbalance on where it grasped it, aspects like that. And when we look at real manipulation tasks, this is very important. So a first step that I took towards this direction is to try to get a robot um, discovering a new way to do a tasks, even if it has partial observability of some of the physical properties of the objects, for example, unknown masks and masses. And I did that by tasking the robot by, for example, assembling this stable tower of blocks. So as a human, if you look at it, you immediately thought that there is very likely a order of steps that you need to follow in order to assemble this tower. For example, this block might be needed before this one. And even that there is possibly a relationship between the masses of these blocks. If this block is a lot heavier than this one, the tower is going to collide. But the robot doesn't have awareness of any of those aspects. It only has a geometric description of what the task is. It knows where the blocks has to be at the end. We also provide the robot with a model for basic actions. So using models like the ones I described before, the robot already know how to pick and place, or for example, stack a block A on top of a block B. And with this kind of information, it can use classical planner like a PDDL to assemble this tower. It can come up with logical sequences of steps that will provide a logically feasible way to assemble this tower in terms of the order of the blocks, even though that is not going to respect the laws of physics. So my approach consisted in providing the robot this demonstration of what the end goal is, together with a number of objects to be able to accomplish that task. However, the masses are not revealed to the robot. We also provide the robot with this geometric model of how to execute the simple actions. And it also has access to a PDDL planner to come up with these logical sequences. Additionally, it has access to a simulator with a physics engine in which it can attempt this task many times until it discovers a new way to do the task that works with these parameters. Then the output of this is a sequence of steps of the way of the model I described before that tend to be successful in this scenario. I call that a robust strategy. What this method is about is to use Monte Carlo tree search to build a set of possibilities based on the PDDL options to assemble this tower. So the Monte Carlo tree search is used to perform interleaf task and motion planning. So for a given PDDL strategy, for example, put first A, then B, C, or D, there are many strategies like that. For a given one, that would be a branch of the tree. The robot is going to go from state to state by checking if the inverse kinematic of the end position is feasible. Then it will come up with a plan to do that, execute the plan on the simulator, and see the output of the action, which is not known a priori because it doesn't have a model of these objects. By going through the tree on the Monte Carlo tree search way, it will prune very quickly the branches that are unfeasible because the strategy doesn't work with that particular scenario. And it will come up with a final successful or more likely to be successful strategy. And the idea is that in the future, it could try to execute this task on the real world. So here you can see the Optimus robot on the Pi-Bullet physics engine, showing sort of the more successful strategy that it found in that tree. Oops. So with that work, I was very motivated by what are the uses of simulation in robotics and human-robot interaction, how we can better exploit these environments to learn useful manipulation or navigation tasks that we can later execute on the real world. So in the robotics community, there is a lot of discussion about what is the utility of simulation, if it is valid or invalid. So I wanted to have a little section in which I more conceptually describe what are the uses that I see for robotics and specifically for HRI. I think one of the reasons there is a lot of discussion about this is that we're probably talking on different languages. And we have to first specify what is the goal of the specific research question that we have at hand. And that might better define if simulation is helpful or is not. Sometimes people is talking about training, some people is talking about mental simulation, and that this is why the discussions, I think, don't converge sometimes. So recently, there have been a big push in both academia and industry to create new simulators that are more realistic, both in physics and photorealism. Here in our lab, at the Stanford Vision Lab, we have a large effort to work on or develop the iGibson simulator that stands for Interactive Gibson, which specializes in having larger scenes, for example, homes, in which the distribution of objects resembles that of the real world, and also aims to achieve photorealism. That I collected here a number of examples. You can see, for example, 3D World. I know it's an effort, a big effort at MIT. It's a very interesting simulator. But also more recently, we have seen a push in trying to insert humans in the simulations, right? Here you can see NVIDIA, Isaac, or Virtual Home here at MIT as well. And I wanted to reflect a little bit on the uses or how we can better exploit this type of simulation for human-robot interaction. So with that, I just wanted to summarize 4 use cases that I see for robotics. And these are the ones that I think people is not agreeing when these discussions are happening. So 2 main uses of robotic simulation that has been pushed specifically by the reinforcement learning community are robot learning and robot testing, right? These are the ones that we are mostly familiar with. In robot learning, you provide an environment for the robot. It's like a playground for training algorithms. So there's no expectation that that is reality, probably. For robot testing in simulation, now you can perform, you can take advantage of the fact that you can use the simulator very fast to do extensive testing as a proxy for quantifying the robustness of your solutions, or even for discovering corner cases that you didn't imagine. Depending on the research question, this testing might be replacing reality, or it might be just a proxy for reality, but then you still plan to move into reality, and then the predictability of sim to real takes a lot of importance. So then there is the discussion of how valid it is, this testing, and if then we need to move into reality and it looks different. I think one of the answers to that is the difference between direct sim to real or having some representations in the middle, some mid representations that will perhaps further enable these sim to real transfers. So other 2 cases I think people talk a little bit less about, but I'm super interested in, is mental simulation. So for example, in this case, the simulation is not reality, it's not training. It is instead a container for the mental models and forward simulations that intelligent agents can perform. So it's not a replacement of reality, it's instead sort of a parallel simulation that the robot can be running. There are some discussions about the speed that you would need. But perhaps as the robot is in real life, perhaps also interacting with a human, it can be in parallel be running these forward simulations. It is hypothesized that humans can do this. And I wonder what would be the utility of having a schema like that for robotics. And then finally, a 4th case that I see is about having these simulation environments for immersing humans. For example, virtual reality in highly realistic scenarios. I think this can cover significant importance for human-robot interaction and user studies. Here you would be able to collect human demonstrations. You can have humans and humans collocated to provide these demonstrations, or you can have humans collocated with AI agents, right? So you can have human-robot interaction, demonstrations, or testing. Something that I'm excited about in this direction is that it would enable to scale up the data collection in human-robot interaction. So in our field, typically the experiments are of a small size, and this is typically a consequence of the complexity of implementing these types of experiments. But if we could achieve a more standard and generalizable way of running these experiments, I think that would be very beneficial, especially to be able to compare across different experiments or to replicate experiments. And finally, if we think about specifically VR, you have the advantages that you can create events or visualizations that you wouldn't be able to create in real life for these experiments. So that's another advantage of this approach of simulation. So those were sort of conceptual discussion of 4 different ways in which I see the utility of simulation for robotics and HRI. Specifically for HRI, if we want to implement those 2 types of versions that I discussed, it would be very beneficial to advance the realism of simulation. So if you look at this 5-bullet simulation I showed you before, done in 2018, it's still very basic. The blocks are single color. It doesn't reflect the real world in some sense. It is actually an abstraction of it. If you look at the image before, which is from the iGibson simulator in our lab, it is more photorealistic. The distribution of objects resembles that of real world. So I think in order to use the simulators in that way, it would be very beneficial to continue the direction of increasing the realism of them. However, that is not the only solution. I'll talk about that a little bit. Then specifically for HRI, there is this topic about adding interactions with humans and other AI agents in simulation. If you have this type of systems on virtual reality that I described, you could implement sort of human teaching or data collection for human-robot interaction. You can have now testing of real virtual world in which you can have a human testing the collaborative policy of the robot in simulation. And another direction I think is important for HRI is that of adding multi-agent environments for robot learning. So if you see typically at the efforts in reinforcement learning, it is typically for single agent learning embedded in these simulators. What if now we can move into having multi-agent environments in which some of these agents might try to attempt simulating humans? And of course, I'm aware this is extremely challenging. This is why we don't use a lot of simulation in human-robot interaction. Simulating the human would be sort of the ultimate challenge, right? We can make decisions on the fly. It's really hard to have a model for our behavior. However, it might be possible to have basic behaviors of these interactions. At the end of the day, that is the same we're doing with manipulation in simulation. We have basic abstract representations of what is happening, and perhaps we can learn a basic policy that then we can deploy and perhaps fine tune in reality. So this is a long-term view of having these sort of simulations for HRI, but I think is a direction that is worth to explore. So in this direction of multi-agent simulation, I started studying these aspects on the context of social robot navigation, and I'll describe this next. So in the context of social robot navigation, we asked if we could use a deep reinforcement learning solution in which the robot will use simulation to learn how to navigate politely around pedestrians. So if you think about the problem of robot navigation, I'll give you a familiar scenario for some of you. If you think about the problem of robot navigation in general, or just navigation, imagine you want to go here from Stara to Area 4, which is, by the way, one of my favorite navigation tasks in the world because there is good coffee in Area 4. So if you think about this problem, it is true that we can have a super photorealistic 3D model of the scene in simulation, right? However, if you think about it, I feel like humans have sort of a more basic, lower dimensional, less detailed model to think about these problems. So even though that might be beneficial for simulation or for some aspects, we still need to analyze if the problem actually requires a more abstract representation. So for the case of navigation, it might be something like this, which I got from Google Maps. There are the streets, maybe the blocks that you're familiar with. And if you're already familiar with the environment, you can high level come up with a plan, right? A series of waypoints on the route on how to get from A to B. If you think about social navigation, about these pedestrians, this is really a local problem. You are not thinking about the pedestrians from the start. This is something that even though you have your global plan, you will negotiate these local interactions as you go, right? Furthermore, there are also sort of these basic behavioral templates that we already have. Like crossing the street is a little bit different from going straight or even from entering the door of area 4. We have sort of different policies for negotiating this interaction with other humans that are predefined. We have already practiced them and we employ them when we recognize a particular environment. So this hierarchy of having the global plan and these local interactions with pedestrians lends itself very well, again, to using learning and planning together. Similar to what I described for manipulation, I think we can use planning here for having this global plan, as the global trajectory plan, and learning for having a policy for the local interactions on how to maneuver around pedestrians. So if you look at the problem of social navigation in general, it has been, most of the research have tackled the problem in open spaces, where the robot has sort of more space to navigate around humans. However, if you look at typical indoor environments, these spaces are more constrained and they have less space for the robot to maneuver. This makes the problem a little bit less, a little bit harder, as in these typical templates like these corridors or crosswalks or door exits are really a little bit harder because of the constrained maneuverability that you have around pedestrians. So we asked if we could use the existence of these basic templates to leverage them in the learning process in our deep reinforcement learning algorithm. And this is both for the geometric templates, but also for the type of interactions that emerge from these templates. The interactions in the corridor are different from the crosses, for example. So for investigating this problem, we created some simulation environments in iGibson using the physics engine PyBullet, in which we have this multi-agent system with an arbitrary number of pedestrians. Every pedestrian has an initial and an end goal for themselves. These simulated pedestrians use a basic social forces model called ORCA, which is a joint optimization between all the pedestrians and guarantees no collision among them. Also, the ORCA pedestrians have awareness of the robot. So there is already some sense of collaboration from the pedestrians to the robot. The pedestrian will also try to accommodate the robot as they move together. And as a robot platform, we have the Jackrobot differential drive robot, which is a custom designed robot in our lab. So as I described, I wanted to explore this compositionality principle about the use of these very simplified abstract templates to learn how to generalize to more complex environments. And the more complex environments can be more complex in two ways. One way is to go into a more complex geometry that exhibits composition of the simple templates. For example, compositions of corridors or door exits and the crosses, which you might have in simple templates in which you train. The second, it is more complex geometrically, but it's still like a straight walls world, right? Everything is abstract. And if you're using LiDAR, what you get back is a straight LiDAR profile. The second type of generalization is also more complex in geometry, but it's also coming from a 3D reconstruction of a real site, such as an apartment or a supermarket. So here, there is more noise in the type of LiDAR profile that you get. There are objects, there are details in the doors and the walls that are not always and almost never are straight like this type of walls. However, I said to ask if training in these simplified templates can help you generalize to that as a way to see if these templates are actually like a basis to understand our navigation instead of having to train in the complex environment already. So our solution is a deep policy, but it's also guided by motion planning. So I try to motivate this with the original example of the map. The idea is that we're gonna use a motion planner to get waypoints to go from A to B. So those waypoints are here represented by these red poles. We can, these waypoints are input to our policy network. So it's being guided by motion planning. The other inputs to the policy network are the goal, so where the robot is trying to go. And also as perceptual input, we have a 1D LiDAR. So this policy is trained with the guidance of the motion planner. We're using the soft actor critic deep RL algorithm, which is of policy and it acts in continuous space. And we have a combination of dense and sparse reward. So we positively reward the robot, obviously, for accomplishing the goal. There is a small penalty for time step to encourage the robot to get to the goal in the minimum time possible. Of course, we penalize for colliding either with pedestrians or with the walls. There is a positive potential reward for approaching the next waypoint. And of course, discrete reward for getting to each one of the waypoints. So we tested this compositionality idea by doing this multi-layout training. So we're gonna train the robot in a set of simplified templates, like for example, these three over here. And in fact, we find that if we try to generalize to the more complex layout that exhibits a combination of these basic elements, we can generalize with a better result, significant better result than trying to generalize from training in simplified environments that don't exhibit all the types of geometric elements and interactions on the target layout. These are some of the training curves for our system using 5 different seats. These are for the first multi-layout training I showed you before. We also compared this solution with a planner. In this case, is a planner directly from the ROSNAV stack. And we did that by stress testing the system in both our policy or the planner with increasing number of pedestrians, here from 4 to 16. And here you see videos, both videos are from our policy running with increasing number of pedestrians. So what we found is that for all cases, the policy which uses learning and planning performs better than using planning only. And we also found that they sort of decrease their performance similarly. However, they do it for different reasons. The planner usually, when it's failing, is because it is failing to find a solution in the amount of time that it has. And this is known as the freezing robot problem. In other words, it fails to find a feasible solution, to compute a feasible solution as the pedestrians are moving. And then it's just freezing there. It's not moving because it doesn't find the solution. For the learning plus planning, what is happening is not that it doesn't find a solution, but that it does in fact collide. So we did test this policy without having any safety stop in order to be able to compare the raw policy. However, for any deployment, you will actually have a LiDAR or sensing enforced safety stop. In which case, what would happen is that the policy will be forced to stop, pedestrians will continue moving, and the robot would be able to proceed. This is a short video showing the second type of generalization I described, in which we train only in these simplified straight walls and then generalized to a 3D reconstruction of an apartment and also a supermarket. So the robot learns these nice behaviors like stopping and waiting for the pedestrians here represented by these blue cylinders. Sometimes he backs up to give space for the pedestrians to continue. And he learns behaviors that are very useful for this type of negotiations with around pedestrians. We found also that training in these simplified environments generalize better to these 3D meshes than training directly on the meshes. And I think that speaks about the importance of having these bases of these abstract representations that are more important to the task than instead more basic to the task than overfitting to a particular environment. And by the way, it is hypothesized that humans do this too. We heavily rely on an abstract representation of the layout to localize and navigate in our natural environments. I show you many results in simulation. However, of course, my dream is to move this to the real platform. Here you can see Jack Rabbit navigating around. We have tested that we can move policies that act in velocity space from a learned policy to the real robot. However, this project unfortunately overlapped with this difficult time worldwide of COVID, so we really weren't able yet to move the social policy to the robot. However, I wanted to show you sort of our final idea, and hopefully we can do it at some point. So now I would like to move into discussing some of my ongoing work, briefly next steps, and also a few ideas that I have in how these topics of embodied AI can help us in understanding some of the principles of natural intelligence. So some of the next steps for the social navigation line of work that I just described is to actually move into vision and semantic information. So I just spent like 20 minutes arguing about having these basic representations that are still not photorealistic. And I think that's the basis of simulation. However, when we want to move into real environments and learn other types of behaviors that depends on the context, for example, this problem of the door I've been discussing, or just behaviors that really depend on the type of environment that you are, using the LiDAR only is not going to be enough. This LiDAR was enough to test the principle about the layouts, but it's never going to provide further information that we do have when we perform navigation in human environments. So one idea to go further into this direction is to actually add visual perception and the semantics of the environment. So nowadays, we fortunately count with more information and labeled data sets about what are the specific elements that we can find in these human environments. So combining these two things, we can help the robot learn the correlations between specific behaviors and specific elements. And then hopefully the robot is going to be able to acquire a behavior such as, okay, this is a door. I know it's a door entrance. If a person is coming, we need to negotiate this in a special way, which is different from a different context or semantic context. So I think those next steps are going to be really important. By the way, if you're really interested in these topics of embodied AI, for example, social navigation or other embodied AI tasks, such as point nav or object navigation, I suggest you keep an eye on the embodied AI workshop, which is coming up in CVPR 2021. There might be some interesting things in which you can participate there. So feel free to check out that in the near future. So now moving into collaborative manipulation from this experience of interactions in simulation, my current work is also looking at the problem of collaborative planning, or how to plan for a collaborative task. So this is very similar to the task and motion planning problem, which is usually solved by a single agent, right? And it's difficult enough that way. if now we move into how to solve these problems in collaboration, it just becomes really, really challenging. Yet humans seem to really solve this problem efficiently and effortlessly in our daily tasks. We collaborate with people at home, in offices, and we can do these tasks as part of our daily life. So I really wonder what are the mechanisms that enable this ability. So for that, I'm looking at planning with heuristics, but also with neural architectures and latent spaces with recurrence that have shown to be able to generate sequential tasks for single agent. So how we can move that into tasks that are now collaborative, I think would be very interesting. On that line, I wanted to show you a little bit of ongoing work. This is joint work with Stanford PhD student Chen Wang and Karen Liu and my postdoc advisor Silvio Savarese. So here, I'll quickly show you just, this is a human-human demonstration. Each human is operating each of these creepers. And the question here is, can we go from human-human collaborative demonstrations to now learn a collaborative policy for one of these agents? In other words, can one of these grippers be replaced with a collaborative robot? And is this information enough to learn how to do it? Not only that, this is a sequential collaborative task. So there are two steps. First, there is a handover, and then the other gripper is going to open the drawer, and it gets help by putting the object on the drawer. So all these kinds of behaviors at the motion level, for example, if you look at the problem of handover, it is typically solved by looking at the problem from the robotics point of view only. So if we're going to perform handover, the robotics point of view is track the object and find the grasping position. But that doesn't talk about the fact that one of the parts is a human. So if you look at human-human handover, there is really a choreography in which both agents are moving simultaneously. So it's a joint process. And that is something that I would like to get to tap further into with these collaborative policies. This work is in a very early stage, and I'm not able to share further details yet, but stay tuned to see what comes out of it. Oops. Okay, and then finally, this is my last topic. I would like to discuss a little bit how we can use this trend in simulation and embodied AI and using what we have learned in robotics to now understand more basic or fundamental principles of natural intelligence. So I think robotics is a field that is uniquely equipped to help with this task. And the reason is that we are by excellence a field that has been thinking about agents that can perform both action and perception in the loop, as opposed to using only, for example, computer vision and only perception. In robotics, I think we tend to focus a lot in the task itself. And one of the reasons for this is that it is challenging and we still don't have general representations, for example, for manipulation that can solve general tasks. So that's one reason we sometimes overfit or over-specify things that are only for a specific domain or task. However, I think with these recent advances in computation and simulation, we can really start using this action, perception, and interactions between agents to understand some more basic principles of what are the common skills that enable some of the cognitive tasks, instead of thinking in robotics about how to solve a specific task. And I call these building blocks of intelligence. So these building blocks that I'm talking about are general neural architectures or training algorithms or approaches for reasoning, heuristics, data structures, memory, and so on. Instead of thinking about the specific task, thinking higher level about what are these common architectures that can be reused across different fields. And the theory is that using these building blocks, we can unify them into modular integrations that produce perception, action, representations of the world, intuitive physics, and so on. So one of the reasons I think embodied AI and robotics in general can help with this topic is because of this action perception loop. And I'm gonna give a concrete example in which I think there is a very strong connection that in the future can really help in this particular problem. I'm gonna provide an example. So these synergies between natural intelligence and artificial intelligence have been very fascinating for many people for many years. But recently, we have started to see some concrete progress in exploiting this synergy. So one fascinating example that I think is good to discuss is, for example, this pioneering work from Jamins and Jim DiCarlo, in which they actually found correlates between a neural network, artificial neural network trained for a visual perception task on object recognition. So they found a specific neural correlate between that neural network and activations on actual natural neurons in performing the same task. So I think this is pioneering work on really understanding how something trained for a purely AI task can help understand some process that is going on in nature. So these neural correlates were found only for a perception task. What if we can now use this type of simulation and embodied AI to further use this method, but now not only in perception, but also perception and action? And one particular problem that I think that can be very useful too is to understand this very fascinating fact, a known fact about the modular regions of the brain. So human brain and other primates, the brain is really separated into these regions with functional specificity. For example, for vision, we know we start from the nerve optics and we go back to B1 and then down to the ventral visual pathway. So there are known facts about these different regions. For example, planning is done in prefrontal cortex. So there are known parallels between things that we do in AI and specific regions of the human brain. So by having simulations that have both perception and action, I really think we can exploit this large scale simulation to see if these kind of architectures will emerge. And the specific point I'm trying to make is that this type of very modular architecture is not going to emerge from looking at perception only. We will need to have these simulated agents that can execute multimodal perception, but also action, so that the perception depends on the type of actions you are taking, the same way we do it. For looking at this, at the emergence of these regions, we will need to impose behavioral and environmental constraints, such as the embodiment of the particular agent or any energy consumption. And finally, I would also be excited to explore what is the role of interactions with the world, but also with other intelligent agents in what is the role of those interactions in natural intelligence. At the end, I think we all learn from interactions and never in isolation. So with that, I conclude my talk and I'm looking forward to any questions you might have.
Thank you, Claudia, for the nice talk. Are there any questions?
Sure, I'll ask you a quick question, although I don't know, some people probably have to go. And
yeah, we're a bit past 2 p.m., but.
So I was thinking about the navigation with the pedestrians. And yep. I know that there's some people who have done work in that area where they more explicitly model the mental state of the humans.
Yes.
And I'm wondering if you think that that's ever useful, or that it just with enough training, you kind of learn to factor that out. I mean, you don't have to consider it explicitly.
Yes, I do think it is useful. And I'm going to elaborate about that. If with enough infinite training, you can accomplish the same, I'm not sure, but I don't think it's a relevant question either, because if we can use the model of the mental state of the humans in particular their intentions or predictions of their future motion. If we can use that to bring the training complexity down, then that would be a contribution on itself, instead of trying to just go end to end and just say, yeah, infinite training will solve the same problem. I don't think it's even, it wouldn't even be important. So with respect to modeling, there is important work. For example, John Howard, MIT also have very interesting work on deep learning for social navigation. I think the part in which it will be key to model the mental by mental state, I'm going to say prediction of where they are going. I think that part is going to be important, especially in human environments, in which we can use the semantics and the context of the environment to understand what people might be trying to accomplish. So definitely, if we have a prediction of them, the robot will be able to use that information to more fluently move around the pedestrians. This work that I have so far, it didn't include a prediction of the human. And then the disadvantage that you can concretely see, and that makes me say, yes, it's going to be useful for sure, is that as I explained, these simulated pedestrians, they collaborate with the robot because they are aware of its presence and they will also move around. If you remove that collaboration, our policy would fail. So it means that it is not able to adapt to pedestrians that are not in collaboration. I think if we add that prediction of the motion, then the robot will be able to adapt in that scenario too.
Yeah.
So I think it's definitely important.
Cool, thank you.
Thank you.
Other questions? Following up on this social navigation task, I was surprised by the assertion of the abstract walls being more useful than the meshes themselves.
Yes.
I would understand this if we were to kind of generalize to other meshes, but like if one is in distribution and the other one is kind of a bit out of distribution, even though it's like a basis, I have a tough time wrapping this up.
So what we found is that if you train to be concrete, if you train directly on this mesh, we have two meshes, an apartment and a supermarket, to be very concrete. If you train directly on either mesh, your generalization to the other mesh or other of these toy environments is of less quality than generalizing from the simplified layout.
Oh, so the generalization mesh to mesh is like from apartment mesh to supermarket mesh.
Yes.
Oh, I see. I had missed that.
That is
now it makes a lot more sense.
Yes, and that is low quality compared to training on straight walls, simplified layouts to the supermarket. Awesome. So one reason for that is that I believe the mesh of the apartment didn't exhibit a common template, right?
Right.
Instead, the ones that we design on purpose are more reusable, are more present across human environments. The other reason I think is that if you train directly on the mesh, you might be overfitting to details. Like there is a lot of noise in this like furniture, or like when there is a door, it's not just a straight door, there is a border. So it might be overfitting to that kind of artifact that is not really the basis that will enable you to do a plan on how to navigate in that layout. But it would definitely need further analysis to fully understand the effect, but it's definitely going in that direction.
Awesome.
I have a question. Hi, Claudia. Thank you for a great talk. I have a question actually related to this project. So I could see in the example you gave that when there was a human in the way, the robot would wait until the human moved out of the way, right? How does it make that determination that, okay, first of all, this is a human, and then second of all, it's a human that's going to move out of my way and I can go? Or it's like, no, this person is here, I need to find another way to go around them.
Yeah, that's great. It's actually not reasoning at that level in this moment. So this policy is not aware that that moving thing is a human versus the other parts of the profile being a static object. So really all the reasoning that it can be doing is there is LiDAR returns in front of me. the policy has been allowed to stop and go back in order to not collide. So it will basically wait there because colliding is highly penalized. So if it is in front of it, there is no other way to go. It will just wait there, but it's not going to collide because that's highly penalized. The other option is that the pedestrian moves a little bit and that signals to go back. The moment it goes back, the simulation for the pedestrians will collaborate as well in moving in the space that it might have opened by moving back. So it's happening as a consequence of the simulation running with this collaboration from side to side. As Leslie asked, it would be fundamental to include that notion that the blue cylinders are actually special agents that we need to take care of. But that would require further augmenting that architecture with further inputs. So the moment we go into visual perception, as I described, I think we can add special or concrete tracking of humans versus non-humans, and a model that predicts what they're going to, and then something like you are describing would be possible. And there is work doing that exists already, but they don't happen in constrained environments. So the particular contribution of this was to be able to navigate in tidy human or real world looking environments. Now we want to go into add that as well, the prediction of humans.
Thank you.
Thank you.
Donald, do you have a follow-up question? Maybe his mic is not working. He was asking on the chat if a thermal sensor detection could detect and track humans with a probabilistic model or the same for pets.
Sorry, can you repeat that? Thermal?
Yeah, it's on the chat. So he was asking, couldn't a thermal sensor detect and track humans with a probabilistic model?
You mean a temperature sensor? I'm not sure.
Yeah, that's what I understand.
That's very interesting. Well, if you had a temperature sensor, other than COVID-related diagnosis, you can also detect humans. That's actually very interesting. I mean, using only vision, there are already very good detectors for detecting where a bounding box in 2D and 3D of where humans are located. So it would need some experimentation to understand having vision only versus also the temperature sensor. That sounds very interesting. If that helps you understand how humans are going to behave, that's sort of the prior step, right? Like having sensing, detecting them where they are, and perhaps the semantics of the space helps you know where they are potentially going. That's definitely going to help, right? Like there is some work, I've done some previous work on prediction of human motion, in which we saw that it's relevant not to only track their motion, but only track their possible goals, because that helps inform the prior of where the human might be going. So you have that information as prior, and then the posterior is given by the motion itself.
Awesome.
I had a quick question.
Yeah.
So I was just wondering, how much of a difference would it make if instead of controlling just one robot amongst pedestrians, if you had multiple agents to control and you had to somehow optimize it with the other robots as well as pedestrians?
And do you want to allow the robots to be centralized, control in a centralized manner, or you want each robot to be distributed and therefore take its own decisions separately?
Yeah, I guess distributed, like that would probably help in scaling it.
If it is distributed, I would start by running exactly this with a number of agents, and then trying to train the policy of each one independently. If you allow centralized, then I would look heavily at the multi-agent reinforcement learning literature to see how you can jointly learn the policy for all of them. There is also a very interesting work on not only doing that for navigation, but also perhaps for a collaborative task like moving an object together. So two reinforcement learning agents trying to learn to move an object together. So work like that is what you want to look at for that question.
Thanks.
Any other questions? Awesome.
Just a follow-up question. Could you just give a little bit more detail about the simulator used for the pedestrian social navigation?
For simulating the pedestrians themselves, yeah.
Yeah.
So actually, we used this social forces model called ORCA. It's open source. You can go, if you look at the paper, there's the link to the source code of ORCA, so you can run it. So what ORCA is doing is a joint optimization of all these pedestrians. That joint optimization guarantees that pedestrians are not going to collide with each other, and they're not going to collide with the obstacles in the space. The other thing that it allows is to tell the pedestrians about the existence of the robot. You do that basically by telling ORCA that the robot is another pedestrian. So when a pedestrian is close by the robot, it will try to act around it the same way it acts around other pedestrians. And therefore, there is that collaboration that emerges by the trick of providing this to ORCA. That is with the purposes of simulation, right? To create a realistic simulation that resembles that of a real human walking around the robot, and then you also take your own action to not go into the robot, right? So it's not really a trick that makes the simulation unreal. It's a trick that tries to resemble that mutual collaboration. However, when you do that trick, the robot is not actually participating in the joint optimization. So that's only from the point of view of the pedestrians. The robot is not really taking its actions based on that would be not really learning anything. So the robot is not guaranteed to not collide with them. The robot has to learn its own thing on how to act so that it doesn't collide with other pedestrians. Does that answer the question? Do you have any specific doubt about the...
Yeah, that does answer the question. Thanks a lot.
Definitely take a look. And there are other better simulations that include also planning for the pedestrians. What I think, and is one follow work, is that in order to improve this simulation, we would really need pedestrians that sort of interact in a more human way. If you look at this, you know it's a simulation. There is no way these are humans moving. And so we would like to improve that simulation. One way is to learn generative models from human data, and we have a follow-up project on that. Let's see what turns out from it.
Awesome. Thanks a lot, Claudia.
Thank you. I really appreciate you having me. I have had a really great time. Thank you for the questions.
Bye.